Field of solar PV, there are multiple strands of concurrent research happening around the globe. There is a race to improve efficiency and to reduce cost of solar panels. After all, solar industry caters to a multi-billion-dollar market. But there are very few technologies that have the potential to disrupt the established solar industry, and nanostructured solar cell technology is one of them. The type of solar panels we have on our rooftops are not the most efficient, but they are the most cost-effective. And this is the biggest reason why crystalline silicon solar panels have dominated with more than 90% share. Crystalline silicon solar technology was also helped by the fact that high purity silicon was already being used to produce electronic components. Furthermore, silicon is also one of the most abundant elements on Earth's crust. So, despite the fact that there are solar panels in existence that have more than twice the efficiency, crystalline silicon technology for solar panels still remains the king. The other technologies that have superior efficiencies are thin film gallium arsenide, multi-junction solar cells, and perovskite cells. And likewise, copper indium gallium selenide or SiC solar cells have better temperature coefficient, meaning their efficiency degrades much less when the panels are hot compared to traditional crystalline silicon. However, none of these technologies have taken off for the following reasons. Firstly, because the manufacturing process cost is too high, and secondly, because the material cost is too high. But there is a new technique that has emerged through which the amount of material can be substantially saved, thus reducing costs. This technique is the use of nanostructures for making semiconductors. And one of the nanostructure in use is the nanoconical frustum array. In simple words, we can now make semiconductors in the shape of tiny strands that are less than 50 times the diameter of a human hair. By making the semiconductor in the shape of these filamentary crystals rather than using bulk semiconductor wafers, we can reduce the amount of material used by more than 1,000 times. Or in other words, as Jeffrey Grossman, professor of engineering at MIT puts it, pound for pound, the new solar cells produce up to 1,000 times more power than conventional photovoltaics. There are many other types of nanostructures also being examined, such as nanotubes, nanowires, and fullerenes. Not only less material is used, but nanostructures are also more efficient in absorbing incident light. These nanostructures can also pick up reflected light falling in the vicinity, so they can be sparsely located. Note that one of the reasons why we haven't been able to make use of gallium and indium is because of their small quantity available in the Earth's crust. With nanostructures, however, we can make both indium and gallium go a long way, long enough to disrupt the solar market that will grow to reach $422 billion by the year 2022. Nanostructures will allow less abundant elements to compete and will also improve the efficiency of existing silicon panels. The nanostructures are only a few hundred nanometers in size, which means they cannot be seen with naked eye. They can be etched in a simple one-step process into silicon. The work at Kyoto University has shown that the use of nanoscale semiconductors of etched silicon plates raises the energy conversion rate of solar cells to at least 40%. This is more than twice the efficiency of the best quality solar cells we have in the market. Note that nanostructures concentrate incident solar energy. Therefore, the Shockley-Kaiser limit, which is the limit for maximum theoretical solar cell efficiency for a nanostructured solar cell, is much higher. At present, the use of carbon nanostructures in dye-sensitized solar cells and perovskite cells is also being explored. The use of nanostructures means that we would be able to produce more than double the amount of power than our existing solar panels over the same area. Both the increase in efficiency and reduction in material use translates into lower costs. A price of 0.56 cents per watt is being targeted by one of the manufacturing companies, which is very competitive. How far are we from commercialization? Well, last year in September 2018, the first of the truly black nanostructured prototype cells rolled off the industrial production line. These cells were rated at 20% efficiency, which is not at all a bad starting point for a new technology. It is estimated that panels like these will hit the market within the next 2 years.